So okay, right, ma. In previous class, we were discussing about the module 4, which is power system transients and concept of corona, and the concept of corona phenomenon is explained in the previous lecture. Corona, what is corona? What are the factors that affect the corona? Critical voltages and power loss. So these topics were discussed in the previous lecture, and also we were done the few problems on critical voltage and power loss due to corona. Okay, so now today we are going to discuss about the power system transients and traveling waves. So what are the incidence wave, reflected wave, and types of transients we are going to discuss in this class. So let us see the power system transients. So in your network theory or circuit theory, you would have studied about the transient state analysis for small networks. Okay, for a lumped RL network, RLC network, like that. Okay, you are already studied the transient behavior of some simple circuits. Right now, here in this lecture, we are going to observe the transient behavior of a power system which consisting of a transmission lines, and the transmission line also the electrical parameters, resistance, inductance, and capacitance, all these parameters are uniformly distributed over the transmission line. So those are not lumped parameters. Okay. So in our second unit, third unit, I think, in our third module, so we were discussed about the short, medium, and long transmission line. So while analyzing the short, medium transmission line, we were considered that the transmission line will be having lumped parameters. So and those parameters are connected either in star or delta. So that is, we will discuss about the equivalent pi model and equivalent star model for a medium transmission line. Okay, so but that analysis will not be done for this case, traveling wave analysis. Okay, so now when the transmission line is connected to a voltage source, so the whole line is not energized instantly. Okay, so the transmission line will be having resistance, inductance, capacitance, which are uniformly distributed. Okay, so such a line is energized by one voltage source. The whole line is not instantly energized. So there will be some time elapsed will be there to charge these inductance and capacitance of the transmission lines. Okay. Right, the traveling wave you can also call it as a surge here. So the traveling wave you can also call it a surge. So this surge may be mainly caused due to switching and lightning. So during switching operation or during lightning stroke, a traveling waves would be produced on the transmission line. Okay, and the voltage wave is always accompanied by a current wave. So if there is a voltage wave, so always there will be a current wave also, right? So the voltage wave is always accompanied by a current wave. Okay, and these surges reaches the terminal of the equipments, such as transformers, protective equipments, and if these surges reach those equipment, they may damage them. They may damage them if they are not properly protected. Okay, if the terminal equipments are not properly protected, these waves, these traveling waves which are produced due to switching and lightning may damage the equipment. Okay, so you have to always protect the your equipment from these traveling waves. And also you know that as the waves are traveling along the transmission line, their wave shapes and magnitudes will change. Okay, so this process is called the distortion. Okay, as the wave is traveling from one end to the another end of the transmission line, the wave shape may change its magnitude as well as shape. Okay, this is called the distortion. Okay, now you have to study the traveling waves, and this study of traveling waves will help in knowing the voltages and currents in all the points in the power system network. Okay, so the main aim of this traveling wave analysis is that, so by studying these traveling waves, you can know the what are the voltages and currents in all points in a power systems, such that you can design the insulators, protective equipment, and insulation of the terminal equipment and overall insulation coordination. Okay, so once you know the voltages and currents at all points of the power system network, you can design what are the capacity of insulators, so what are the capacity of protective equipment, so what is the insulation level for an equipment. So like that, these parameters will be known by this traveling wave analysis. Right. So what are the types of transients that are present in the power system? Okay, depending upon the speed of the transients, these are classified into extremely fast transients, medium fast transient, and slow transients. So these extremely fast transients will occur due to surge phenomena, which mainly due to the lightning and switching operation. Okay, so suddenly if the transmission line is switched on and switched off, or there is a lightning stroke on the transmission line, in such a case, the transients will be of very extremely fast. Okay, so the waves produced by those transients will be traveling at a very faster rate. Okay, and the medium fast transients are those transients which are occurring due to short circuit phenomena. Okay, when the transmission line is short circuited, so the transients produced will be having a velocity which is a medium velocity. So those transients you may call it as medium transients, and slow transients will be in case of transient stability. Okay, transient stability analysis when you are doing, so the transients you can consider them as a slow transients. So another important point we have to remember here is that for a steady state operation of the transmission lines, the transmission lines could be represented by lumped parameters. Okay, if you want to observe the steady state behavior of the transmission lines, so the transmission line could be represented by lumped parameters. But if you want to analyze the transient behavior of transmission lines, then you have to represent that transmission line by their actual circuit elements, right? The transmission line which is nothing but a distributed parameters. So a transmission line is a distributed network, you know that. Okay, so that distributed network, if you want to analyze the hello 225. సో 225 ఎవరమ్మా?
ఎస్ సార్.
సో 225 మీకు హోస్ట్ వచ్చింది చూడండి, అది నాకు హోస్ట్ ఇవ్వండి.
ఓకే సార్. సార్ ఆప్షన్ చూపెడతలేదు సార్.
నువ్వు మొబైల్లో లాగిన్ అయ్యావా ల్యాప్టాపా?
మొబైల్ సార్.
మొబైలా? సో ఆప్షన్స్లో నీకు మేక్ హోస్ట్ అని సంథింగ్ ఉంటుంది చూడండి. ఒక నిమిషం. శ్రీకాంత్ సార్
హలో,
అది హోస్ట్ పోయింది సార్.
సార్ ఇచ్చాను సార్.
స్టూడెంట్స్ వాడికి ఓకే
ఇచ్చాను సార్.
వచ్చిందిలేమో వచ్చింది.
ఓకే సార్.
థ్యాంక్ యూ. Okay, is it visible PPT? సో PPT షేర్ అయిందా మీకు కనిపిస్తుందా?
Yes sir.
Okay, right. So now let us see the concept of traveling wave. So a traveling wave in transmission line is nothing but it is a voltage or current wave which propagates from source end to the load end. So during the transient condition, okay. So during the transient period or transient condition, so the voltage or current wave which is traveling from source end to the load end is called the traveling wave. Okay, so these waves travel along the line. So at a velocity which is equal to velocity of light if the line is lossless. So if the transmission line is a lossless transmission line, so the velocity of traveling wave will be approximately equal to velocity of light. Okay, so but practically so there is always exists some losses in the transmission line. So the velocity of propagation of these traveling waves will be somewhat less than the velocity of the light. Okay, so you know the velocity of light which is equal to 3 into 10 power 8 meters per second. So that much amount of speed the wave will travel from source end to the load end. Okay, so to analyze this traveling wave, let us consider a lossless transmission line which is shown in figure. Okay, so lossless transmission line in the sense you are going to neglect the resistance and conductance. Okay, resistance and conductance parameters are neglected. So you will be having only energy storage element which are inductance and capacitance. Okay, so you are only considering the inductance and capacitance of transmission line. You are neglecting the resistance and conductance. So such type of line is called the lossless transmission line. Okay, so in the first figure the representation of lossless transmission line is given. So here one end you will be having the source, another end you will be having the load. Okay, and the source and load is connected with one switch here. Okay, when the switch is closed, the voltage and current waves will be transferred from source to the load. Okay, so the same network, the lossless transmission line network which is shown in figure is represented by an equivalent circuit in the second figure. Okay, so as I said, it is a lossless transmission line, there is no resistance and conductance. You will be having only inductance and capacitance. Okay, so you know that this inductance and capacitance values are values for a transmission line are uniformly distributed over the length of the line. Okay, so like this. So inductance parameter is a series parameter and capacitance is a shunt parameter. Okay, so this lossless transmission line equivalent circuit is given in the second figure, where in the second figure you will be having L1, C1, L2, C2, L3, C3 like that up to some Ln into Ln and Cn. Okay, inductance and capacitance like this. So inductance and capacitance are uniformly distributed. Okay, so now when the switch is closed here, so what happens, the voltage and current will be supplied from this voltage source. Okay, so that means the voltage wave and current waves will start traveling from this source end. Okay, so instead if you observe, whenever the switch is closed, instantly there is no voltage or current at the load. Okay, instantly you will not get the voltage and current at the load end once you switch on this switch. So why? Because you are having the inductance and capacitance here. Okay, so first your inductor has to charge and then capacitor C1. So after charging capacitor C1 to some voltage V, so then the current will be flown to the inductor 2. Okay, so then it will charge the capacitor C2 and then after the capacitor C2 is charged to a voltage V, so then the current will be flows through that inductance L3, and then after it reaches after this capacitance C3 will be charged. Like this process will be continued here. Okay, so that means your voltage and currents, so current will be flowing through the inductor and voltage will be across the capacitor, you can observe. Okay, so this voltage and current waves will be uh, will not be observed instantly at the load, right? So there will be some time elapsed will be there from source to load. Okay, so is it okay, ma? Whenever you close the switch, the voltage and current waves instantly doesn't appear across the load. Okay, so they will be first the inductor, the current will flows through the inductor and it will charge the capacitor C1. So for that, for the capacitor C1 to fully charge up to the voltage, certain voltage V, so there is no flow of current in the inductor 2. Okay, once you get the some voltage level here, so then this inductor will charge and this capacitor will charge. Like this, first section will take some time, and then next section, and then next section, like this it will continue up to the load. So that means your voltage and current waves will be traveling from source end to the load end with some velocity. Okay, right. So to understand this traveling wave propagation, you can observe the one water tank analogy here. Okay, so in this water tank analogy, I'm going to take water tanks here. Okay, here you are having water tanks, and here you are having one tap. So this valve is nothing but switches. Okay, so this is here you will be having one pump which may be the source. So this valve is the switches. Okay, and the current flowing through the inductance, you can consider it the water flow of water. So flow of water is considered as the current flowing through the inductor, and level of the tank will be considered as the voltage across the capacitor. Okay, so I'm going to analyze now. So one single tank represent one section of L and C, another tank another section of L and C. So another tank, another section of L and C. As I said before, until this capacitor is completely charged, you cannot get the current flow here. So if you see this analogy, water tank analogy, so whenever you close or open this valve, so water will fall into the first tank. Okay, water flow will be there. So until this tank is filled up to this level, so that means until the voltage across the capacitor becomes V, so there is no flow of water in this second tank. Okay, so until this first tank is filled up to the some level, so there is no flow of water in the second tank. So whenever it reaches some level, so then only the water flow will be there from tank A to tank B. Okay, again, so instantly this tank C will not get any water. Okay, until the second tank B is getting a water level up to this. So in a similar manner, in an transmission line also, so in a transmission line which are represented with L and C sections, so until your capacitor is charged to a voltage V, this there is no flow of current in the this inductance. Okay, right, whenever there is a flow of current in the this inductance, this capacitor will charge until this capacitor charged up to a voltage, there is no flow of current. Okay, so that means your voltage and current waves will be traveling from source end to load end, or propagating from source end to load end slowly. So not instantly, they will be transferred. Okay, so this is about the water tank analysis for understanding the traveling wave propagation. Okay, propagation of traveling wave. Now if you want to observe the velocity of traveling wave, So at what velocity the wave is traveling. So let us see here. So sorry, one slide is missing here. So before going to that, first you observe the relationship between voltage and current waves. Okay. So you are having a voltage wave, you are having the current wave. So now first you observe the relationship between this voltage wave and current wave. Okay. So for that purpose, let the voltage wave and current wave will be traveling at a distance x in time t. Okay. So your voltage and current waves are traveling a distance x meters in time t seconds. So you assume, right? So therefore, the inductance and capacitance of the line up to your distance x will be considered as Lx and Cx respectively. Okay. So that means your transmission line will be having a distance x here. Right now, let us assume that your voltage and current waves are traveling this distance x in time t seconds. Okay. So now if you take this distance x, so the total inductance up to this distance x will be Lx and capacitance will be Cx. Okay. So L here is the inductance per unit length and C is the capacitance per unit length. Okay. So because of this reason, so up to a distance x, inductance will be Lx and capacitance will be Cx. So now let us assume that the wave travels through a distance dx in time dt. Okay, as we are assumed the line to be a lossless transmission line, so there will be no voltage and current drops will be there. Okay, as a transmission line will be, transmission line is a lossless transmission line, so there is no drop in voltage or current. Okay. So whatever may be the voltage and current at the beginning, the same voltage and current we will get at the after time t also, right? So now the energy stored in the send capacitance. Okay, you are having the inductance, you are having the capacitance. Okay, so the energy stored in the this capacitor, send capacitor, can be determined as like this. The energy, or you can state it as a charge. The charge stored in the sent capacitance can be written as q is equal to v into Cx. Okay, your total capacitance is Cx, so you can q, you know the formula, q is equal to v into C. Okay, here C becomes Cx. Okay, q is equal to v into Cx. In a similar manner, the flux in series inductance can be written as phi is equal to I into Lx. So flux or flux linkages. So flux linkages or flux can be represented with L into I. Here inductance L is, total inductance L here would be Lx. So in place of L, you have to write Lx. So that phi will become Lx into I. Okay. So but you know that current I is equal to dq by d. By definition of current is the rate of change of charge. Okay, so I is equal to dq by dt, you can write. Now in place of q, I am going to write this v into Cx. So then current I will be equal to Cv into dx by dt. So x here is nothing but distance. Okay, so then when distance is differentiated with respect to time, it will become velocity. So dx by dt will be the velocity of the traveling wave. So let us represent this velocity of traveling wave will be small v, mu you can say. Okay, so then this I can be written as I is equal to Cv into small v. Okay, so this here is the velocity of the traveling wave. Okay, so in a similar way, so the voltage developed across the sent capacitance. So if you want to calculate the voltage which is developed across the sent capacitance, so then that V can be written as d phi by dt. So V will be equal to d phi by dt. So here phi here is the I into Lx. Okay. So you substitute this I into Lx in case of this phi. So then V will become equal to I into L into dx by dt. Again dx by dt is V. So which is velocity of light. So V will become equal to I into LV. Okay. So this is voltage developed across the, so not sent capacitance, across the inductance. Okay. So the inductance voltage across inductance is V is equal to d5 by dt. Okay. In place of phi, you are going to write the I into Lx. Okay. So the final value what you are getting here is V is equal to I into L into small v. Okay. So this V is the velocity of light. So now this equation and this equation we are going to divide, so that V by I is equal to IL by CV you are getting. Okay. So now this I and this V going to this side. So you will get V by I whole square is equal to L by C. So that V by I will be equal to square root of L by C. Okay. So now from this equation, what you can say? So V by I is nothing but impedance. Okay. So the impedance of the transmission line will be equal to root L by C. So this impedance you can also call it as a surge impedance. So Z is equal to or characteristics impedance underscore L by C. So characteristics impedance or surge impedance of the transmission line Z is equal to underscore L by C here. Okay. Right. So after getting the surge impedance value, so then you can determine the velocity of traveling wave, right? So to get the velocity of traveling wave, so these two equations 1 and 2, so will be multiplied. Okay. So V and I is equal to CVV into IL into V. Okay. CVV into IL into V. So from this you can write small v square is equal to 1 by LC. So V is equal to underscore it 1 by LC. Okay. So this is the velocity of the traveling wave. Okay. So the equation of velocity of traveling wave small v is equal to underscore it 1 by LC you will get. Okay. So now from the first unit you know that inductance and capacitance values are, so inductance is equal to 2 into 10 to the power minus 7 ln d by r dash. So for simplicity you can call it as simply r, and capacitance C will be equal to 2 pi epsilon by ln d by r. So now we are going to substitute these two here. Okay. So here so then what you will get here is finally is, so the small v will be equal to, so 3 into 10 power minus, sorry 10 to power 8 meters per second. So the velocity of traveling wave value is, so 3 into 10 power 8 meters per second. Okay. So now, so this is for overhead transmission line. So now suppose if you take the underground cables, so then if you are while considering the underground cable, so this epsilon here, so here in case of epsilon is nothing but epsilon naught into epsilon r. So for overhead transmission line, this epsilon r will become equal to 1. So but in case of underground cables, so this epsilon will be having a value more than 1. So in case of that underground cable, the capacitance value will be very high. So because of that reason, the speed of velocity of traveling wave in cable will be less than the overhead transmission line. Okay. So the speed of velocity of traveling wave in underground cables is less than the speed of velocity of traveling wave in overhead transmission lines. Okay. Right. So this is about the traveling wave, concept of traveling wave. So the relationship between the voltage and current waves and the velocity of the traveling wave. So now let us see the some specifications of the traveling waves. Okay. So generally these traveling waves will be represented in many forms, many mathematical forms will be there. So most commonly used representation for the traveling wave will be infinite rectangular or step wave. Okay. So most general representation of a traveling wave will be like an infinite rectangular or a stepped wave. So it will be looking like this. A stepped wave will be looking like this in figure. Okay. So you will be having the wave will be like this. Okay. And this traveling wave will be characterized by four specifications. So those are crest, front, tail, polarity. Okay. So crest of the wave. So crest of the wave is nothing but it is the maximum amplitude of the wave. Okay. So maximum amplitude of the wave, and it is generally expressed as a kilovolts or kiloamperes. If the wave is a voltage wave, units are kilovolts. If the wave is a current wave, then units are kiloamperes. Okay. So whatever may be the wave, so whether it is a voltage wave or current wave, it will be having one maximum amplitude. Okay. So here for this, here you are having the maximum amplitude. So that maximum amplitude of the wave is called the crest of the traveling wave. Okay. So then front, wave front, or you can also call it as wave front. So what is wave front? So wave front is represented in terms of time, and it is the portion of the wave before the crest. Okay. So here you are at a point B, you are having the crest. Okay. So this is the crest point, so which is at a point B. Okay. So now the portion before this crest. Okay. So the portion of the wave, so before the crest, is called the wave front, and it is expressed in terms of time. So from the beginning of the wave to crest of the wave. Okay. So that means here to here. So T1 is the wave front. Okay. So wave front is represented in terms of time. So in a similar manner, another specification is wave tail. Okay. So wave tail is nothing but it is the portion of the wave. So beyond the crest, here before the crest is the front, and beyond the crest is the tail. So that is also from the crest to 50% of the crest value. Okay. That the portion of the wave from this crest point B to a point where the crest 50% of the total crest value is there. Up to that point, you can consider it as the wave tail. Okay. So here T2 you can consider it as a wave tail. So from the beginning to this point. Okay. So the another specification is polarity. Okay. So there will be a polarity of for the crest voltage or voltage value or current value. So this magnitude may be positive or negative. So if it is a positive wave, so then you can represent it as a, so let us simply you take one example. So there is a positive wave which is having 500 kilovolts crest, 1 microsecond front, 25 microseconds time. Correct. So wave front and wave tail both are represented in time only. Okay. So microseconds, 1 microsecond front and 25 microsecond tail, and is having a 500 volts 500 kilovolts crest. Okay. So now if the wave is positive, so in such a case you can represent with one symbol plus. So plus 500 by 1.0 by 25.0. So this is the representation of a traveling wave. Okay. So traveling wave will be represented with, so magnitude, first polarity and its magnitude. So 20, if it is a voltage wave, 250 kilovolts by wave front 1 microsecond by wave tail 25. Okay. So if you are having a current wave, so then plus 300 300 kilovolts, sorry, kiloamperes. So their wavefront may be 2 microseconds and a tail will be 50 microseconds. Okay, like this, the representation of the traveling wave will be there. Okay. So this is about the specifications of a traveling wave. So now let us see the behavior of transmission line to the traveling waves. Okay. So now here onwards we are going to take some conditions of your transmission line, and we are going to observe the behavior of the lines for those conditions, and we will analyze the traveling waves. Okay. So now first case I am taking here is a open-ended line. Okay. So I am taking a transmission line which is having open end. Okay. So the open end transmission line I am going to consider. So for that open end transmission line, how will be the behavior of this line for a traveling wave? Okay. See here. So consider a line with a receiving end as a open circuited. So you see in the figure here, you are going to consider one transmission line, and the receiving end here it is open circuited. Okay, here you are having the voltage source, and here you are also having the one switch here. Okay, so this is the transmission line from here to here. So this transmission line is a distributed network. So inductance and capacitance. So these are uniformly distributed like this. Okay, inductance and capacitance will be there. Okay, so there will be whenever you close the switch, so the voltage wave and current wave will be traveled through this transmission line network from sending end to receiving end, right? So now at the receiving end, if you observe, so there is a change in impedance. Okay, so when there exists a change in impedance at any portion of the transmission line, so then this voltage and current waves will be having some reflection and refractions. Okay, so these we are going to study here. Okay, so right, so whenever a switch S is closed, a voltage and current waves which are having the magnitude V and I respectively will travel towards the open end. Okay, whenever you close the switch, voltage wave and current wave which are having the magnitudes V and I will travel towards the open end. Okay, so and this voltage and current waves will be related by one relation which can be written as V by I is equal to Z. Okay, here Z is the characteristic impedance of the transmission line. Okay, so Z is the characteristic impedance of the transmission line. Now here this voltage V and I, you can say them as a incident waves. Okay, incident waves. Okay, so now these waves will travel from source to this load. Here load is a open circuit. Okay, now here let us consider a small element dx at the last end of the transmission line. Okay, so you are going to consider one last element of the transmission line which is represented as dx. Okay, dx is the last element of the transmission line. Here the wave is going to change its impedance. Okay, up to here you will be having characteristic impedance Z. Okay, so now here as you are having the open circuit, so open circuit in nothing but Z will be infinity resistance or infinity impedance will be there, right? So impedance Z will be changed to infinity. Okay, so at this element dx there is a change in impedance. Okay, so which is infinite impedance as you see, as it is a open circuited line, right? Now, so if you observe the electromagnetic energy stored in the element dx, so here this element dx will be having inductance always as well as capacitance. Okay, so this inductance this small element dx is having some inductance and capacitance here, and the inductance will store the energy in the form of the magnetic field, and capacitance will store the energy in the form of electric field. Okay, so the electromagnetic energy stored by the element dx can be written as half into L into dx into I square. Okay, so if there is a inductance, you know that. Okay, if there is inductance, energy stored will be equal to half into L into I square. Okay, so you know this formula from the fundamentals. Okay, so in case of capacitance, the energy stored in the capacitance will be half into CV square. Okay, so this energy is the electromagnetic energy and this energy is the electrostatic energy. Okay, so now for this small element dx, the inductance will be equal to L into dx. So in place of L, you are going to write L into dx. So here for capacitance, for the same small element, capacitance will be C into dx. Okay, so in place of C, you are going to write C into dx. Okay, so now you'll be having electromagnetic energy stored in the element dx, which is equal to half into L dx into I square, and electrostatic energy as half into C dx into V square. Okay, so now as here there is a open circuit, the current I will become equal to 0. Okay, so in open circuit there will be no flow of current, right? So the current at open end will be 0. So now when current is 0, what happens to this energy? Electromagnetic energy. Electromagnetic energy will vanish. Okay, so but as per the conservation of energy, there will be uh, no loss for the energy, right? So then what happens? So when this becomes 0, what is going to happen here? Okay, actually the energy is not going to lost here. So the energy will be transferred from this electromagnetic energy to electrostatic energy. Okay, so at the open end, as the current is becoming 0, this electromagnetic energy will be changed to electrostatic energy. Okay, so this change will make the voltage at the receiving end to be changed, right? So that voltage, change in voltage, let us assume that E. Okay, let us assume change in voltage will be small e. Okay, so in such a case, this total energy will be changed into electrostatic energy. So that means half into L into dx I square. So this energy is going to become as half into C into dx into E square here. Okay, so change in voltage is, yeah, voltage is here small e. So in place of V you will get small e square. So from this you can write, you can get the E will be E by I is whole square is equal to L by C. So from this E is equal to what you will get? So E is equal to I into square root of LC you will get, right? Square root of L by C you will get. So the this under square root L by C will be, you can call it as characteristic impedance Z. So E here will be equal to I into Z. Okay, so I into Z is nothing but again V here. So from the this equation, okay, so V is equal to I into Z. Okay, so first in here small e is equal to I into Z you will get. So this small e will be equal to the V only. So that means the change in potential will be here, you can say that it will be equal to V. Okay, so the voltage of the open end is now raised by voltage V volts. So now the total voltage at the open end line, open end when it reaches this end will be equal to V plus V, which is equal to 2V. Is it okay, ma'am? So here your traveling wave V and I will be produced at the source end and these will travel towards here. Okay, as we are considering the lossless transmission line, so there will be no change in magnitude for this voltage and current. So but whenever this voltage and current waves will reaches the open circuited end, so then this voltage will become doubled. Okay, here you will get voltage will be raised to 2V and current will be become equal to 0. At open end line, current will become equal to 0 and voltage will become equal to 2V here. Okay, so why? Because at the open ended line, so the electromagnetic energy stored in the element will become equal to static energy. That means electromagnetic energy is changed into electrostatic energy. Okay, and the change in voltage V, small v will be equal to V. So this V plus this V. So total you will get 2V, right? So the voltage at the end of the transmission line will be having 2V and current will be equal to 0. Okay. Okay, as I said before, so the wave which starts traveling from the line means which S is closed could be considered as the incident wave. Okay, so the waves. So whenever you close the switch, the waves which are traveling from source end to the load end, so those waves will be considered as a incident waves. Incident wave. And after the wave reaches the open end, so there is a rise in potential V. So that rise in potential V could be considered as a due to a wave which is reflected at the open end. Okay, and the actual voltage at the open end could be considered as the refracted wave or transmitted wave. Okay, so here we will be having three types of waves: incident wave, a reflected wave, and a refracted wave. Okay, so if you take one transmission line and the transmission line is terminated with some resistance Z, let us assume. So this transmission line will be having a characteristic impedance of Z. Okay, so now here V and I are the voltage and current waves which are traveling from the source end, and whenever it reaches this end of the transmission line, so now so one wave may be reflected, one wave may be transmitted. So the waves which are transmitted is called the transmitted waves. Okay, and the waves which are reflected is called the reflected wave. Okay, and these waves which are coming from the source end V and I, these are called the incident waves. Okay, so you'll be having incident wave, you'll be having reflected wave, and you'll be having refracted wave. So this is refracted wave, you can also call it as a transmitted wave. So the value of refracted or transmitted wave is equal to sum of incident wave and reflected wave. Sum of incident wave and reflected wave. So and for open circuited line, traveling wave is reflected back with positive sign. Okay, if you observe from the previous discussion, so the voltage is going to be double. So that means so the incident wave V at the open circuited end will be going to change its magnitude to TV. So the change in voltage is nothing but here the voltage wave, there is a one wave which is reflected back here. Okay, as there is an open end, there is no transmitted voltage. Okay, so this voltage V will be reflected back with a positive sign, and you can call the coefficient of this reflection will be considered as a unity. So similarly, if you observe for the current wave, as soon as the current wave reaches the open circuited end, so that current wave will become 0. Okay, as soon as the current wave reaches the open end, the current at the open end will be 0, and this could be explained by saying that a current wave of I magnitude travels back over the transmission line. So this means open-ended line will be having a current wave which is reflected with negative sign, and coefficient of reflection will be unity. Okay, you see here if you observe the voltage and current relations for for a line for open-ended case. So from this diagram you can understand. Okay, so first initially voltage wave V and I, these are the incident waves. Okay, you are having one transmission line, one switch, and end is open circuited. Here open circuited it is there. Okay, so you are going to consider this length. So the total length will be, let us assume that L will be the total length. So whenever you close the switch, so this voltage wave and current will start traveling from the source end. Okay, so this V and I are the incident waves, you can say. Okay. So whenever these waves travel to a distance L, what happens? So this voltage V will become equal to 2V. Okay, and the current will become equal to 0. Okay. So what actually here happening is here. So voltage and current, these will be travel towards like this at this open end. So you'll be having a reflected voltage as well as a reflected current. So reflected voltage will be having a positive sign and current will be having a negative sign. So why? Because for open circuit, open-ended line, current will be zero. So when that zero current will be having, so when it will be having, so whenever you are having a current wave which is having a negative sign. Okay, so here this side you are getting positive voltage, sorry, positive current. Okay, here this side you are getting negative current, so that total current will be zero. And voltage wave, this incident wave and voltage, reflected voltage, this will be two, will be having the only positive sign, so the total voltage will be 2V. Okay, so those are represented in the voltage and current wave, which are represented here. Okay, so when the wave travels at a distance 2L, so that means your wave is going from source end to load end, which is open circuited. So from here to here it travels and then it will come back. So total, if L is the total length, so forward and reverse total length is 2L. So at 2L length, so your voltage will be equal to 2V and current will be equal to 0. Okay, so now just after the length, what happens here? Actually generally this source voltage is always V only one. So because of that reason, again a voltage with a negative sign will be reflected from the source here and the voltage becomes V, and in a similar manner current wave with the negative sign will be reflected back. Okay, so like this, after a length of 4L, so the voltage and current both will become equal to 0. Okay, right. So this is about the transmission line which is having open-ended line. So now suppose if the transmission line is short circuited at the end, so what happens to traveling wave? Okay, so here I am going to consider the transmission line and the receiving end will be short circuited. So previously it is open circuited. Now I am considering it to be short circuited. Okay, so now whenever you close the switch, voltage and current waves will be traveling from source end to the load end. So those waves, voltage and current waves, will be having a magnitude V and I respectively, and these are related with some small relation V by I is equal to Z, where Z is the characteristic impedance. Okay, so now electromagnetic energy. So here also you will be having electromagnetic energy and electrostatic energy. So in electromagnetic energy represented with half L into dx into I square. So electrostatic energy half into C dx into V square, right? So here in this case, at the receiving end, so as it is a short circuited, here voltage becomes 0 and current will become double. Okay. So reverse to the previous case. In open circuited case, current will be 0, voltage is doubled. So here in short circuited condition, voltage will become 0 and current will be doubled here. Okay. So that means here, in this case, short circuited case, electrostatic energy is converted into electromagnetic energy. Okay. So now the same relation, electrostatic energy is half C dx V square. This will be changed to half into L dx into small I square. So I is the changing current here. Okay. So from this, you can write I as a V by Z, which is equal to I. So what you can say here, the changing current I is a capital I. Okay. So this means there is a increase in the current in I amperes. So because of that reason, total current at the short circuited end will be equal to 2 amperes. So for short circuited end, the current wave will be reflected back with positive sign, and coefficient of reflection will be the unity, and the voltage wave is at the shorted end is be 0. So which is nothing but a voltage of wave of negative V will be there. Okay. So here for a short circuited case, V and I are the incident waves if you observe. So which are traveling this side. So whenever it reaches the short circuited end, so V is going to be 0. So how V will become 0? If there is a voltage wave which is having negative sign on the same magnitude, and current will become doubled. So that means, so there is a reflected current wave which is having the positive sign. So this I and I will become 2I, and minus V and V will become 0. Okay, this is how it happens. Okay. So the current wave in short circuited end is reflected back with positive sign, whereas the voltage wave is reflected with the negative sign. And coefficient of reflection for the both case will be unity only. Right? How we will get the coefficient of reflection or unity, we will discuss in next class. Okay. So if you observe the variation of voltage and current waves for the short circuited end, once you observe here, you observe here first at t is equal to 0 plus, you will be having voltage wave and current wave whose magnitudes are V and I respectively. Now after the length L, okay, up to the length L, V and I will be there, right? As the end is short circuited, after T is equal to L plus what will be there? So there will be a reflected voltage wave will be there, and with negative sign, and reflected current wave will be with the positive sign. So this voltage will become 0 and current will become 2A at the source end. So that means when the wave travels 2L distance, voltage becomes 0 and current will becomes doubled. Right? So then after 2L plus, again another voltage wave will be traveled towards the short circuited end, and current wave will be travels to the short circuited end. That means current will become 3I here. Okay, and it will be traveled towards the short circuited end. Okay, after 3L distance, this will become voltage will be the V only, and current will be total 3I. And after 3I plus, again one voltage with negative sign will be reflected, and power current with positive sign will be there. So the current will be become 4I, and voltage again becomes 0. Okay, so see here, man. In case of sharp circuited case, the current is going on increasing. Okay, so when the wave is traveling a distance which is equal to 2L, the current is doubled here. So when the distance traveled by the wave is 4L, the current is becoming 4I. So in the similar manner, if you go on increasing the length, so that means for 6L, the current will be 6I. Like that, you will get. Okay. So current will go on increasing in case of short circuited case. Okay. So now